Morning everyone. So we're going to continue our final review with our chapter 9 on redox chemistry or electrochemistry. Remember, redox is actually two half reactions in one. First, we actually start off with the oxidation part of it. Oxidation, by definition, is a species that ends up losing electrons, so this is a loss of electrons. We know electrons aren't stable in nature, charges in general aren't stable. So basically we're looking at, for a redox reaction, the electrons that are lost by one chemical are actually picked up, are actually reducing another chemical. That's the first part here. For a reduction reaction here, this one here then implies a gain of electrons. Usually when you think of something that's being reduced, it's being taken away. But in this case here, we're actually grabbing things that are negative. What's being taken away here is actually my charge is actually coming down. So similar to our acid-base chapter here, a redox reaction is essentially a transfer of electrons. Basically, one person is going to donate the electrons, one person is going to pick up the electrons, although unlike the acid-base section, we're not necessarily going to be a one-to-one ratio. It's not just a one proton transfer. We may actually need to do some balancing, lowest common multiple, to actually figure out how many electrons were actually passed. But there we go, we get our redox chemistry. For electrochemistry in general, it's looking at the changing of energy between chemical forms to electrical forms. We're going to start off with the one side here on spontaneous chemical reactions, reactions that just happen by themselves. They generate for me a positive E cell, so they give me a positive voltage by running a spontaneous equation. For those equations there, we're going to call that a voltaic cell or a Daniell cell. And then towards the end of this chapter here, we flipped it around. What if there's a reaction that I want, but just based on the delta G, it doesn't want to react spontaneously as written? So in that case there, we actually use a electrical source from the outside. We actually do electrolysis. And for electrolysis, basically, we're using electrical energy to force a non-spontaneous reaction to occur. Right now, it's non-spontaneous because the E naught is actually negative. So basically it's those two headings here, but it's trying to compare these two features, trying to link chemical reactions to electrical energy and vice versa. So a couple easy ways for you to learn this section here. We say some corny acronyms here. Leo the lion says grr. Okay. Leo the lion here, that actually stands for the loss of electrons is oxidation. 5 years from now, you're going to forget all about this redox stuff, but you'll still remember this. Leo the lion says grr, whereas grr or jr is this gain of electrons. If you remember, this first little bit here had a lot of definitions. Gain of electrons is reduction. So it's a transfer of electrons from the thing being oxidized to the thing that's being reduced. Careful, we are looking at just the reactants in this case. So let's say I have chemical A and chemical B. Let's say that A actually passes its electrons over to B. I would then say A has currently been oxidized, whereas B has been reduced. B has picked up the electrons. Afterwards, you may become totally different chemicals, C and D. They're sort of similar to the conjugate forms left over in the acid-base chapter. Sure, the electrons have now passed over. It may not be super easy to recognize the chemical. Maybe it's bonded with other things and whatnot. But potentially, the electrons could be passed the other way. They could potentially oxidize and reduce. But specifically, we are looking mainly at just the reactant side. If things weren't bad enough, we then define some other terms here. We might know what the reactions oxidation and reduction look like. We're now going to hire some agents to do our job. An agent is someone that's going to help you get oxidized or someone that helps you get reduced. So in this case here, if A got oxidized upon losing electrons, B is actually called the oxidizing agent. This chemical here by itself ends up getting reduced, but its job is to allow A to get oxidized. Its job is to sit around waiting for electrons so that whenever A is ready to lose those electrons, it's ready to take those electrons up. Remember, you can't have two oxidizing agents. You can't have both willing to give up electrons or both willing to take electrons. You need to have one of the other. So similarly for the reducing agent here, the thing that gets oxidized is actually called the reducing agent. That's not the definition I would use as a definition. As an agent, I'm helping someone else end up getting reduced. So there's a terminology there for you, but mainly we are looking at the reactant side. Especially when your reactions got a little more complicated, especially when we start throwing in ionic compounds, covalent compounds, oxidation number, or what's sometimes called oxidation state. This is something that we had just arbitrarily decided on a list of rules to try to figure out what charges the chemicals actually have in the compound that it's in. And depending if this charge goes up or goes down, we can actually very easily predict whether it's oxidized or reduced. In the past, they used to say oxidation state is the Roman numeral, oxidation number is just the digit, but they've been using them synonymously here. It should be more obvious. Basically, we're going to assume the entire compound itself is ionic, and basically we just assign these charges here. So let's just have a look at a few compounds here. Let's say the compound here, NaClO. All right. So realistically, this compound here, definitely the Na to the ClO part, the Na would be positive, the ClO would be a polyatomic grouping. That would be an ionic bond between the metal and the nonmetal. However, for the covalent part here, the Cl and the O, these are nonmetal nonmetal, they just share electrons. That's another way they could ask this question, which of these molecules contain both ionic and covalent? We're looking for something like this that has a polyatomic. What we're going to do with oxidation number and oxidation state is we're going to come along and we're going to say, let's pretend the entire thing is ionic. Because we're dealing with gaining electrons and changing charges, let's just pretend to assign charges. So what we're going to do is we have a bunch of rules here. We have rules like elemental forms. The way they normally appear, we just call them 0. Let's say Na is 0, or phosphorus with a 4, that's 0. Basically, everything is 0 in the way that they normally appear. If I have just a simple ion, you can just give it the simple charge. Na plus is going to be a charge of +1. If I have phosphorus -3, that's going to be a charge of -3. You'll notice the charge actually depends on what form it's actually taking. Then we need a couple ones that will be constant across the board. These are ones that typically their charges are really well known. For example, alkalis are known to be +1, oxygen is known to be -2, and we try to, by deduction, figure out all the rest. So for example here, Na is given a +1 charge. For this oxidation stuff, you have to have the sign first and then the number after. On the mark scheme, they actually will mark you wrong if you just put 1+. Like I said, 9 times out of 10 it doesn't matter, but just get in the habit of doing the sign first so that when it matters, like in this case your oxidation number, you'll have it correct. I know realistically the covalent compound as a whole has a negative charge, but what we're doing for oxidation numbers, we're saying, well, the oxygen part of this compound would have been a -2. What might chlorine have to be right now so that overall, we notice that this compound here is canceled out as charges. Overall, the whole charge is 0, so chlorine would actually have to be +1 in this case. Again, sign first and the number. Chlorine does not really have a +1. This is even different from the formal charge stuff we did in chapter 4. But in this case here, this is the charge. If pretending the entire thing is ionic, it would be sort of like a +1. So if this compound here later on gave me a Cl2, Cl2 is how it appears in nature. If chlorine goes from a 1 to a 0, by dropping oxidation number, that implies a reduction. If it went from, let's say, 0 to 1 instead, that would be an oxidation, because that's actually it, going up in oxidation number. So a couple of different easy ways to actually figure out oxidation numbers. Things for you to be careful of. Oxidation number is quoted per atom. So although this chlorine here is diatomic, I would actually say this is 0 and this is 0. Make sure the sign first and the number. And then if you can track these changes here, an oxidation will imply this oxidation number increases, whereas if the oxidation number or oxidation drops, it's actually decreasing. Sometimes they actually use this oxidation number to actually rename some of the compounds that we did before. So in our chapter 3, we did a compound, let's say H2SO4. We would have started off just saying SO4 is sulfate, F or pH doesn't matter. Sulfate would have been changed to the ending sulfuric acid, ic acid. What they would call it is actually using the oxidation number. Well, hydrogen is a +1, oxygen is a -2, each O is -2, but in total, 2 of them would make a +2 for hydrogen, 4 times -2 would make a -8. What is the charge that sulfur would have to cancel the charge? It's like sulfur has a +6 charge. They're going to, in textbooks, actually call it sulfuric 6 acid. We actually only saw this Roman numeral in front of the metal name when things were multivalent. Things actually have more than one charge, but they're using it in this case here to identify the oxidation state. If you do a comparison of H2SO3, we can equally well call it sulfuric acid. I would have called it sulfurous acid, changing ending OUS acid, but in the textbook they'll call it sulfuric 4 acid because the sulfur in this compound is actually a 4. So you actually need to check compound by compound. The only oxidation numbers that are constant across the board are one of these rules here. Most of these rules are okay, but there are the odd compound. Let's say I have a metal hydride when hydrogen decides to be a nonmetal. For example, sodium hydride here, they can't both be 1, or else they add to a total charge of +2. If I let the sodium, that rule came first, let that be +1. Hydrogen, in the off circumstance, it might be -1. Oxygen here typically is supposed to be -2. Most times that's true. Let's take a peroxide like H2O2. H is going to be +1. That rule came first. The O can't be negative 2 because I don't have any overall charge. In this case here, the O would be a negative 1. You'll notice in all of this, I put the sign first and the number. So if the question, especially for multiple choice, is just asking you, is the thing oxidized or reduced? What I would do first is I would find the oxidation numbers of exactly everything. So I'm going to assign oxidation numbers for everything. I'm going to try to figure out whether the oxidation number goes up or goes down. If it goes up, oxidize. If it goes down, reduced. I'll only balance it if they ask you for it. Remember, we learned 2 different methods of balancing. All they're going to ask you in the test is they're just going to say, balance this equation. What are the sum of coefficients if you need it? Make sure you add up any ones that you might have. Totally up to you whether you do half reaction method or oxidation number method. Let me just do one for example for you here. Let's do U plus 4 and MnO4 minus becomes Mn plus 2 and UO2 2 plus. They're a little bit easier to you in IB that we only expect acidic conditions. So we're going to find, as we do our 2 methods, we're actually going to find we're going to have an excess of H plus, totally no problem. So in this case here, I'm going to go through, I'm going to separate the half reactions. So this is the half reaction method. Basically, I look for things that look similar. So I would expect, let's say, the U plus 4 to become the other U compound. The Mn compound here to be condensed into the other Mn compound here. There's for balancing using half reaction method, the hint is major hydroxide. That's sort of the ordering that we're going to do it. Don't forget this step of doing the major atoms first. Major atoms are everything that's not O or H. We're going to deal with those afterwards. In this case, I have 1 U, 1 U, 1 Mn, 1 Mn, totally okay. For the O's, because a lot of these take place in aqueous solution, we add water. In this case here, we have 2 O's. So I'm going to add 2 waters here, 4 O's. I'm going to add 4 waters on this side. For the H's, I'm going to add H plus because we can assume that it's acidic. I'm going to add those H pluses there. I now have 4 H's because of the water, no H's here, so plus 4 H plus. On this side, no H's, 8 H's, so I'm going to have 8 H pluses. There's no guarantee that when you add one to one side, it doesn't mean the next one has to be added to the other side. It really depends on the chemical. And then because both of these are half reactions, we can have free electrons balancing the charge. So we want to make sure the total charge, they don't both have to be 0, but the left side has to match to the right side. So in terms of the overall charge, uranium currently has a plus 4 here. Over here, I have a plus 2 and an extra 4 pluses here. So I have 6 plus in total. I'm going to take the higher charge and bring it down by adding 2 electrons. In this case here, I have 8 positive minus 1, so I have positive 7 plus 2. So this would end up being 5 electrons. On your data booklet here, the half reactions are already balanced as half equations. To get back to the full equation, if the electrons are on the right-hand side, we know it's an oxidation. If the electrons end up on the left-hand side, this chemical, again, we're specifically looking at the reactants. The U4 plus over the course of the reaction has lost the 2 electrons. Those electrons end up getting picked up by permanganate. It's these 2 things that are getting oxidized and reduced. It just turns out this is what we're left over with afterwards. We don't want to have any free electrons at the end of the day, so I want to do lowest common multiple. 2 and 5 both go into 10. So let's imagine taking this first equation times 5, this bottom equation times 2, and basically you just scale the whole equation up. So this becomes a horrendous mess here. 10 waters and 5 U plus 4. I've already set it up so the electrons cancel, so you don't need to worry about those ones. 2 times H plus would actually give you 16 H plus and 2 permanganate. That's on the left-hand side. On the right-hand side, double check my numbers, 5 UO2 plus 2 and 20 H plus. Then ends up giving you 2 manganese and 8 waters. Because the half equations were balanced separately, it's totally possible at this point you now have waters on both sides and H pluses on both sides. The numbers don't have to exactly match, but you can cancel as many as will cancel. So in this case, I have 8 waters. I can make this one here a 2. In this case here, I have 16 H pluses, and this one is a 20 H plus. So this one here would be a 4 H plus. At that point, it should be balanced in acidic. Usually I want to check for balancing of number, make sure all the atoms are accounted for, but if you're running out of time, just add up all the charges. If the charges are correct, pretty much you're okay. We've only done acidic and we'll always only do acidic, but just for completeness sake here for Chem 12, in case they had asked you the question, instead of doing it for basic, you would do exactly the same thing as I just did for acidic here, but basic means there's not an excess of H plus. I can't guarantee there's going to be a bunch of H pluses left over. So what we're going to do instead is we're going to do some algebra. Because I have 4 H pluses, if it were basic, and only if it's basic, I'm going to add 4 OH minus on both sides. In some sense, the H plus and the hydroxide do cancel out. They don't disappear though. they end up recreating 4 waters, and that 4 waters can be cancelled out with 2 of those waters, leaving it with a 2. If I can just summarize it, so for basic, uranium plus 4 plus the 4 hydroxide, try to write this a little more neat so you can see, this becomes 5 UO2 plus 2. I only have 2 waters left over. The order doesn't matter as long as it's on the correct side. Plus it to 2 Mn plus 2. If I'm running out of time, I would just check the charges. Hopefully they match up. 5 times 2 is 10, plus the 4 here, 14 plus. Over here I have 20, minus 4, minus 2. What is it? I'm sorry, 20 minus 4 minus 2. Does that match up? I'll assume they do. Okay, so 4 and 2. Right. So that way we balance in basic. If you find that they have no H pluses, it can work in both acidic or basic, but you're going to find because I added H pluses in that equation, usually you would need to add hydroxide. The other way of doing this last step, this part here is only if basic. The other way of doing it is you can actually add the water equation. Because I had 4 H pluses left over here, I could have added an equation, let's say 4 H plus and 4 hydroxide is in equilibrium with 4 waters, and in that case the H plus also cancels out the H plus. So you could add the self-ionization of water. That's another way of looking at it. That's balancing using the half reaction method. I'm just going to sketch out for you how does the oxidation number method work. Usually I try oxidation number method first. In general, unfortunately, even though it's faster, people tend to make more mistakes, and the part of the problem is actually really early on is just to make sure your major atoms are balanced. So major atoms, I'm not going to do this one completely, but I'm going to see 2 chlorines here, 1 sulfur, I had to balance it. You go through, you do oxidation numbers for absolutely everything. Again, they're not going to force you to balance it one way or the other. These ones here are 0, these ones here are -1, sulfur is like a +4 here, sulfur here is a +6. I'm going to look at the oxidation number change. The chlorine goes from 0 to -1. It drops, so I know it's a reduction. Sulfur goes from 4 to 6, so it goes up, so it's oxidation. That's good. One wants to lose, one wants to gain. But in this case here, because of the per atom nature, the chlorine is actually a diatomic molecule here. It's going to still be accounted for, still going to be 2 chlorines, but you have to imagine one loses 1 and the other loses 1. In total, this one here is already scaled up by 2. I'm already losing a -2 already. Even before you do any least common multiple stuff, in this case I actually don't have to do it because it's 2 and 2, before you try to match up those changes, you want to make sure I scale it up based on the major atoms. And then if at this point I still needed to least common multiple, if I needed to say multiply by 3, which I don't, I would multiply everything involved in that equation by 3, including that 2 that I added earlier. In this case here, because 2 and 2, all that's worked out already, now we're going to add water. Add water to balance the O, and then add H pluses to balance the H's. Again, the nice thing about this is I haven't broken up half reactions. I don't need to put it back together at the end of the day. It already is giving me the overall, does the H plus go total on the left side or total on the right hand side. So make sure you do practice the balancing question. We will only need to do acidic. Then that's basically half the story. The other half of the story here is actually how do we actually set this up so that we can actually taper the electrical energy off of it. So again, we talked about there's 2 different setups. We've spent the most time talking about spontaneous reactions here. This first part here, again, electrochemical cell, they now redefine that as the umbrella term. For a battery cell, we're actually looking at what's called a voltaic cell or a Daniell cell. Sometimes you're going to be asked, what's the voltage in the Daniell cell? It just means spontaneous. And then let's compare that totally different the other way around. We still call it electrolytic, but electrochemical is now the umbrella term for both of these together. Essentially for electrochemical cell, a couple of key features. We said it has a positive voltage. It's running a chemical reaction spontaneously. You just mix it together and then basically the reaction happens. Because the reaction happens so quickly, you're going to want to have 2 compartments. Now this could really be 1 beaker with a semi-permeable membrane in between, but typically you have 2. If you know which side is which, we typically put the anode on the left side and the cathode on the right-hand side. We need an electrode. An electrode is a metal plate that can temporarily conduct the electrons for us. We're going to be dealing with kind of ions and solutions, but in terms of real batteries, they might actually play around with the state of matter. They might make it out of some porous sort of pasty material so that when you knock this over, it doesn't have problems with transporting liquids. The reactions itself will still be exactly the same. On the anode side, basically the anode as a definition is the site of oxidation. You can memorize that with N-ox caret. So at the anode, at that metal plate oxidation occurs, something loses electrons. It could be the metal itself dropping off its electrons on the plate and jumping off into solution. Or it could be just something else in solution. It might just swim up close. If that's where the electrons are dropped off, it might end up just kind of leaving as well. As long as electrons get dropped off there, we can still call it the anode. Because these are not directly connected, I need to connect it with an external wire. Careful, electrons always flow anode to cathode. And careful, they only flow through the wire. Electrons never enter the solution. This side here is at risk of becoming overly positive. We're going to use our salt bridge as a sort of on-off switch. The job of the salt bridge here is to maintain electrical neutrality, is to make sure neither side is getting overly positive or overly negative. We use those U-tubes to try to connect them. It can be as simple as a piece of paper that's adsorbed with some salt solution. Usually the salt solution we use is KNO3 or even sodium chloride. I want to use some chemicals that are so bad at oxidizing and reducing, such low reduction and oxidation potentials that they won't interfere with the one that we actually want. On the other side here, we have the gain of electrons. So cathode, similarly, is a site of reduction. That's when things end up picking up electrons. Usually when that happens, something will solidify. So maybe I'm going to have like X as a metal here, and I'm going to solidify. It's going to actually eventually solidify on top of the surface here, and we can make some qualitative observations. If we end up forming a solid, we can say the mass increases. If we end up forming a gas, we can say there's bubbles. If I produce H plus or I lose H plus, there may be changes in pH. Those are some qualitative things I can see on either electrode. Nothing you need to memorize because you do have those balance equations here. Let's just flip over to the data booklet here. This is the most modern version of the data booklet. So instead of separating into two, making it really hard to read, we actually have everything just separated into one. Notice that these are still written here. These are the chemicals that are currently oxidized. Going left to right, I'm picking up electrons. That's called reduction. So they could call it a standard reduction potential going to the right. So this one going to the right is at a negative 3.04. The best guy that's reducing is actually this one going to the right. Now, there is no such thing as a reducer. Okay, it's the chemical that gets reduced. We're going to use that language here. Because this thing is going to get reduced, this one here is an oxidizing agent. And because he's not very good at his job, the voltage here is actually negative. We're actually getting the weakest oxidizing agent here, and we actually get stronger as I go downwards. There is none of these that actually go 100%, unlike the acid-base table, so they are all at equilibrium. So any of these equations can be read left to right or right to left. But once you find out which one it is, you're just going to do a one-way arrow. So if you remember, we're going to always start from this, start from the bottom left, because that's going to be the best guy that gains electrons. You go upwards and you find your match. Let's say I have copper solution, iron solution, aluminum solution. The first time you find your match, this guy here is going to one-way arrow. It's going to generate this voltage for you, and the other ones are going to be spectators. The other ones are not as good as the first match that you found, so spectators. These half equations by themselves are already balanced, so you see some coefficients already, but especially when you do piece together both half reactions back together, you might actually need to do lowest common multiple again. So start from the bottom left, and then similarly start from the top right. Even though the lithium plus ion was really bad at getting reduced as a negative voltage, the lithium as a metal is actually really good at going backwards. Anytime I flip it the other way, if I would have lost 3.04 going this way, anytime I reverse the reaction, I'm going to rewrite it right to left. Let's say lithium is now going to become lithium and electron, like what happens in the lithium ion battery here. The voltage ends up picking up a positive 3.04 volts. Right, so we start from the top right. This is the best guy that gets oxidized, so we actually use the terminology here, strongest reducing agent. So we start from the top right. We may not necessarily have lithium metal. I skip my way downwards. I'm going to look for having a first match. Maybe I have zinc, maybe I have copper, maybe I have some bromide as well. All right. Once I find that first match, the other guys are going to be spectators. For a Daniell cell or voltaic cell, you're going to find for spontaneous, you're going to have lower on the left and higher, pen would work here, higher on the right. So by the time you find your matches, I found this guy, he's going to go forwards. I found this guy, he's going to go backwards. You're going to find that this reaction is lower than the other reaction. That's going to guarantee that overall, the voltage there ends up being positive or overall spontaneous. Just to flip over when we do non-spontaneous here, Non-spontaneous, I'm going to do exactly the same thing. I'm going to start from who's the best guy that gets reduced, but by the time you find your first match, it might end up being the water, it might end up being some of these leftover ions here. You find your best competitor, but by the time you find that reaction, you're going to find that this reaction on the left is actually higher than by the time you start from the top right, go downwards. By the time you find some of these ones and it's actually going backwards, you're going to actually find that the reactions are actually swap places. If that happens, you're going to find that maybe overall, individually, the delta E's aren't negative yet, but definitely when you add the two of those, the E and L actually ends up being negative. Okay. But I'm doing those two just both in succession here just to show you we read the table in exactly the same fashion. We always start from the bottom left and go upwards, start from the top right and go down, find your first match. Anything else are spectators. One thing to caution you is make sure you look exactly for the chemical that we have. So for example, if I have a solution, I have an iron plate, and I'm told I have iron plus 3 solution, I'm going to look for exactly Fe. I'm going to look for exactly Fe plus 3. I might need to worry about water if this is an electrolytic cell. Water interferes a lot. Water is super annoying. But in this case here, I don't have iron 2. So wherever I see iron 2, I have to skip over it. I don't have it. Similarly, some of these equations here are a little more complicated. Let's say this one here in the middle, if you can see it. This one here does require sulfate, so I might have sulfate in the solution, but it also requires acidic solutions. So unless they tell me I have, say, acidified H2SO4, I know that's an acid already, let's even make it like Li2SO4. If they don't confirm for me that it's acid, I don't know that there's H+, I can't use this equation. So you want to look for the best guy reducing, bottom left, to the best guy oxidizing, find your matches to figure out what the overall voltage is going to be. Remember, these voltages here are relative. They're relative to the standard hydrogen cell. Make sure you can draw the standard hydrogen potential for me. So all potentials are relative. All these voltages are relative to the standard hydrogen electrode, usually called the She. And essentially, if you look back at our notes here, the standard hydrogen electrode, unfortunately, hydrogen is not a solid, so I can't get a chunk of hydrogen. But I would make this plate something conductive, maybe platinum or carbon, something that's inert. And therefore, either in my reaction, I bubble in hydrogen gas. I put in hydrogen in its sort of stable form. Hydrogen gas, I'm at 1 bar of pressure. I have 1 molar solution of H+. So either the reaction goes forward, where H2 drops off electrons and jumps into solution with H+, or some of them that are worse than hydrogen, maybe the H+ does the opposite. It runs up to platinum, gains those electrons, and then reform hydrogen. We just chose one of the reactions, and we called that voltage there 0. It has that not symbol because we're at standard state, so that contains some of these 1 bar, 1 molar. We usually do things at 298 Kelvin, although that's not technically in the definition there. But that's our standard hydrogen cell. There are some cells, let's say these ones down here. These ones here are much better at reducing than hydrogen, so they have a positive voltage relative to hydrogen. These ones here, which are not as good as hydrogen, doesn't mean they actually generate negative voltage. If it's going to give me negative voltage, why would I bother building the battery this way? But it just means I have, let's say, negative 0.13. It just means 0.13 less volts than hydrogen. And evidently for a battery, this is the battery at initial conditions. So this is when everything is at standard states. But as the reaction occurs and as we actually start changing the amount of chemicals, changing initial and the initial concentrations, the voltage actually drops. In fact, by the time we actually hit an equilibrium, there's no overall tendency for me to go forwards anymore. Overall, the voltage is 0, and the voltage is just a dead battery. One other note here on that standard reduction potential, because voltage is already defined as the work per number of electrons, as I scale this equation, let's say when I do Lowes call multiple, if I end up needing to multiply this by 2, while it is true I'm going to get twice as much work, twice the drop, twice the number of joules picked up, but I also will double the number of charge carriers. So overall, long story short, this E voltage doesn't change when you scale things up. They just add when you add up the oxidation and reduction. Careful of the signs. I would just look at this table. Whenever I do the oxidation, I would flip the sign of it, and therefore I can just add whatever the reduction is, add it to the oxidation. So let's just flush through some of these notes here. I mentioned most of it already. We talked about it needing a salt bridge to complete the circuit. It's only ions that actually travel. In general, anions, which are negative, anions typically go to the side that's at risk of becoming positive, whereas cations typically flow towards the cathode. In terms of the signs of the electrodes here, you notice the sort of direction here. In this case here, we say that the anode is actually negative for a Daniell cell, a cathode is actually positive. The reason why the anode is negative is because the electrons are being dropped off. Lots of negative density is building up there. All that negatives, all of them hate each other. They're going to push each other away, and they're going to go towards the positive side. This was different signs compared to electrolytic, which we'll talk about in a second here. We talked about needing inert electrodes, like for the standard hydrogen cell, I can't get a solid chunk of hydrogen, so let's use platinum and carbon. They're so bad at actually reacting, they just provide a temporary surface to hold the electrons for me here. We have the standard reduction potentials, so that's why we have the E0 symbol. We have it relative to hydrogen. Out of all the cells I could pick, I just chose one of them. I called that 0 volts, and basically I compared everything to that. We talked about when we multiply reactions, we don't scale up the E0 because I also double the charge carriers. In our energy option, we actually looked at some of these reactions in a little more detail. So some of you are more familiar with, in this case here, our lead acid batteries here in our cars. We have lead going from a 0 state to a +2 state. That's a gain, so that's an oxidation. Or lead O2, which is +4, going down to a +2 state, that's a reduction reaction. Again, the electron transfer occurs based on our reactants. In this case, it turns out they both go to the same chemical. It's sort of like a disproportionation reaction. In this case here, the PbSO4 unfortunately ends up coating the 2 electrodes in that battery. When you recharge your battery or jumpstart the battery, all you're trying to do is trying to get rid of some of that PbSO4 coating. You're trying to get fresh lead surface and fresh lead for oxide surface again so that it can discharge again. So some of these cells, majority of them are one direction, so they're called primary cells. They can't be recharged. Nowadays, we want to be more environmentally conscious, so we want to be able to do renewable energies, rechargeable batteries if we can. Quick note on corrosion here. Corrosion basically happens when metals get oxidized. For example, if I have iron as a metal, if iron is put in the presence of oxygen, it's at risk of becoming like a charge from iron, iron 2 or iron 3 with some oxide, any number of combinations of formulas like that. It could be rusted aluminum, things like that. Ways that we can prevent iron from occurring here, because iron needs to be in the presence of oxygen. If, let's say, I have a car made out of iron, if I have a layer of paint, basically the paint here is nonpolar. It actually separates the oxygen from the iron, so the oxygen can't actually touch where the iron is. That's one way of preventing corrosion. However, if you have a chip on that paint job there, the oxygen is now exposed to the iron. Also in wet environments, that also helps it cause rust as well. Rusting was our example of a spontaneous reaction. Nobody wants it to occur, but it's also a very slow reaction. What we can do, chemically speaking, is we can cathodically protect it. We can force it using a sacrificial anode, using something else that will oxidize. Maybe it's a cheaper metal than iron. We're going to sacrifice, let something else do the oxidation. Let's say aluminum here. Aluminum actually oxidizes easier than iron does. Because aluminum is going to oxidize, the iron has no chance of actually oxidizing. It's going to be a spectator. I don't know what charge it's going to be, but the iron is going to be forced. It remains in the reduced state, and that's called cathodic protection. We force the iron to be the cathode, so we keep it in the 0 state, in the elemental state, and it can't actually form rust. So in that case, that's called cathodic protection, or using a sacrificial anode to actually minimize rust. Then we switch over to electrolytic. I already mentioned on the table, it's actually fairly similar. It's just the 2 reactions will cross over. We're going to get a non-spontaneous reaction. You don't need a salt bridge because it's non-spontaneous, so typically you're just going to have one thing. We had applied it to electroplating. So if I have a metal, let's say this is our carbon, it's inert. Let's say I want to plate it out with another metal. Essentially, all I want, you just sort of think about the target in mind. Let's say I want to nickel plate it. So I'm going to take nickel. I want nickel to reduce on its surface. I want the mass to increase. I want it to coat this carbon on the surface. I want the carbon to actually be the cathode. If you look at the directions here, the the anode would actually have to be the positive side. You actually have a lot of control over which side is positive or negative because it's up to me to put in the external power source. I'm going to put in the long line and the short line. I'm going to put in the positive side. The positive side is now the anode, so that any electrons that get dropped off there get picked up towards the positive side, kicked through the battery, and then nickel can then reduce on this side here. Nickel is going to gain those 2 electrons to form nickel solid. That's all we need for the plating reaction, but to be really clever, let's also make the anode side out of fresh nickel as well. As nickel is going to oxidize, nickel is going to replenish the nickel 2 that's in solution. As long as I don't run on nickel 2, more of it can actually plate on the surface. If you really try to do this using a voltage, we can try to compare our overall E0 cell. Typically, because of efficiencies, we are going to actually need more voltage than even that. In this case here, oxidation and reduction, overall the E cell is actually 0, but we can actually play around with the molarities. We did a little bit of this using the Nernst equation in our energy option here, and even if their molarities differ, there is going to be a potential for it to transfer. Nickel is going to jump from the anode plate to the metal plate. So in that case, there's electroplating. One thing to be careful of as an exception, careful of this overpotential effect. Really, we only saw the overpotential for chloride and bromide. Essentially, especially when we look, it happens on both sides, but as we look at the water reaction, we were expecting the strongest things to be on the top right. Water appears by itself a couple of times. Water appears over here. Water appears, should be another place here, maybe as a hydroxide here, but water appears a couple times. If you compare water's ability to oxidize and chlorides, the voltage would tell you water should be able to oxidize first. It's just experimentally we find this one oxidizes first. So due to overpotential, it still has to be down here because the voltage is a little bit lower. But due to overpotential, in IB they're going to say in concentrated, any chloride concentrations, the chloride, in this case here as I have it, oxidizes before water. And in a similar fashion on the other side here, you might find the water equation. So there's water. Technically speaking, if we had, actually I don't think we need too much on this side here. Yeah, okay. But if technically speaking, you might have chloride and bromide that might potentially reduce as well. Those ones, based on number, they should have reacted after water does, but in fact what ends up happening experimentally because of overpotential, that potential is needed to generate some charges in solution, get the reaction going. So in concentrated cases, the chloride actually reacts first. If they say dilute, you can use water reacts first. All right. So in a nutshell, that's sort of the redox chapter here. Lastly here, I just want to do one quick overview of delta G again. We actually now have 3 different ways of analyzing reactions. So delta G back in chapter 5, so far we said delta G is supposed to be negative. When this is negative, that means spontaneous. Based on our redox chemistry here, we actually have a couple of different equations. For the redox chemistry, we didn't use this equation too much, but Gibbs free energy is actually equal to negative NF E0 as well. That formula I think is on your formula sheet here. If the delta G is negative, if we're spontaneous, because of this negative, that means your voltage there has to be positive. So the E cell being positive would actually imply spontaneous as well. So that's a nice link between the two of them here. The N in this case here refers to mole of electrons. This F here stands for Faraday's constant. This is the number of coulombs, turns out to be 96500 coulombs per mole of electrons. And this mole of electrons is in the balance equation. We'll do a practice question for that a little bit later on. But basically we have, because of that pesky little negative here, should have been a highlighter. Because of that pesky little negative, the E0 direction is actually going to be opposite. The more negative the delta G, the more positive the E cell is going to be. That's one equation that we work with. The other equation we can link it to is delta G is also equal to equation 1, equation 2. The delta G is also equal to negative RT ln K. Slightly derived form. Again, we did a little bit more detail in our energy option, but again, because of that pesky negative, if I want my delta G to be very negative, that means my equilibrium constant has to be really big. That means when I do a product over reactant ratio, I'm going to favor products. I'm going to have more products than reactants. How this last one here can be seen here, we can actually plot a graph of just free energy versus our reaction coordinate. The reaction coordinate is just reactants on the left and products on the right. Strangely enough, for energies, we always define 0 to be when charges are at infinity. So I'm going to put that there to be 0. I'm just plotting the actual free energy, so I'm not plotting change here. So as reactants, I would have some negative energy. So maybe I have negative 10 kilojoules of energy. That's the amount of energy I have available for work. Because this delta G, I'm under the impression that overall the delta G is negative. By the time I end up forming products, I'm going to end up with a smaller negative value. Let's say negative 100 kilojoules. So it's a little bit strange why it's negative to begin with, but what I see here is I'm going to lose even more energy. We're going to spontaneously go from a high free energy, a smaller negative number, to a much larger negative number. And this one here, being the delta G, that's a negative delta G here. And that part there actually tells me how much free energy do I have available for work. Because of this relationship between delta G and K, we're actually going to find mixtures are always going to be the equilibrium position. Mixtures, this is going to be equilibrium position. You can imagine as reactants, we have a negative delta G as you fall towards, so delta G is less than 0, as you fall towards this equilibrium position. When I have pure products, I can't make as much of a mess as if I had two different chemicals. The delta G is also negative going towards this equilibrium position. However, in this formula, what it says is the more negative the delta G, the bigger the equilibrium constant is. And what that's going to do is it's going to take this equilibrium position and it's going to shift it very, very close to the product side. Back in chapter 5, we threw around a number of about 30. Anything beyond delta G, any less than negative 30 or so, pretty much the equilibrium is basically 100%. This one here completely goes to completion. Let's flip the picture around here. As the battery starts using up some of the chemicals, as I slowly lose my reactants, this number here gradually drops. I pick up more products. This one gradually increases. I'm going to end up having some equilibrium. At that point there, we have no tendency to go forwards anymore. I'm going to just hit, not necessarily going to be 50-50, but I'm going to have a dead battery when we're at equilibrium. What if we had the opposite? What if we had a positive delta G? So I have, let's say, our negative 100 again. With a very positive delta G, maybe it's negative 10 here. Because the delta G value, because the change in Gibbs free energy is actually positive, I know it's not spontaneous. And in this case here, we actually have the equilibrium lying a lot closer to the reactants. This one may be a 0% reaction, maybe 1% reaction. Definitely has a hard time actually going forwards. And that's how you understand just based on the actual free energy change versus time or versus the reaction proceeding. We don't want a equilibrium situation because equilibrium is actually a dead battery. One last little throw out for this part here, for this free energy stuff here, we found if I have a reaction, let's say copper 2 and 2 electrons becomes copper, we found because of these equations we can actually solve, let's say how much mass of copper ends up getting produced. If I end up giving you, let's say 1.5 amperes of current for, let's say 3 hours of time, what we found we had to do was we had to take the current and the time. Charge is actually given by the current times the time. You need to do your converting of units here. This ampere here is a joule per second, which means this one needs to convert to seconds. Once I find the charge, I punch it through Faraday's constant. So take the number of charges, multiply it by Faraday's constant because that's going to tell you, divide it by Faraday's constant. That's going to tell you how many moles of electrons that I'm transferring. In this case here, because 2 electrons for every 1 mole of copper solid that gets produced. In that case there we can figure out, well, how many moles of copper solid, take the moles that we find from the first step. We use the balanced equation. My balanced equation says 2 electrons make 1 copper solid, and then you can find mass just using molar mass afterwards. So have a look at that last question there as well. We can actually quantitatively compare how much mass is actually generated. Okay, so that ends off our redox chapter. If you have any questions, just let me know. Thanks, guys.